Hello, let's go through one more problem from the 2026 British Informatics Olympiad. Today it's pie in the sky. So this is the statement. As usual, you can pause and read the problem if you'd like, but I'm going to go through it here. So you're given a graph. And you have to find the number of edges in that graph that are in at least one minimum spanning tree. So that's the problem. You can state it quite concisely. So let me explain what that means, in case you don't know some of the words, or in case you don't know what that means. So this is a graph at the top here, and a minimum spanning tree is just a tree using a subset of the edges of that graph. So I mean, if there are n nodes, then you have to use n-1 edges, obviously. So to make it a tree, so 4 nodes, 3 edges in this case. And it's a minimal spanning tree. That's a spanning tree of the graph. And then a minimal spanning tree is one that's total cost is lowest. So in this case, we've got this graph. Here are 3 different spanning trees shown in blue. And this one has a total edge weight of 4. Let me do that in a different color. This one has a total edge weight of 4. This one also has a total edge weight of 4. And the point of a spanning tree is that it connects all the nodes together. It's a tree connecting all the nodes. And this one has a total edge weight of 8. So this is actually not minimal because the other 2 are better. This one's not minimal, but the other 2 are minimal. So the answer to this problem, I mean, there are actually more minimal spanning trees in this. For this graph, there's one more. But so for each edge, we basically just want to find whether or not it is possible. It is in at least one of these. So, for example, this edge with a 2 on it, labeled on it, is in both of these actually. So that means this is in a minimum spanning tree, and so are obviously this one, and this one. But the 6 here, it's possible to show that it's in no spanning tree, minimal spanning tree. So in this case, the answer is 4. Right? We have 4 edges that are in at least one minimal spanning tree. So now we have to do that in the general case. Okay, so now how do we find this number of edges? Right, so if we take a graph, now I'm going to draw something more abstract. So let's say we have some sort of graph. Well, one thing that you can do is just find a spanning tree, right? If you find a minimal spanning tree, sorry, let's find one minimal spanning tree. And we can do that with either Prim's or Kruskal's algorithms. Let's say we use Kruskal's, but that doesn't really matter. So Kruskal's just involves considering all the edges in increasing order of weight. So you take, say, these edges first, the ones with weight 1, then 2, then 6. And so you go through the edges in that order, and then for each edge, you include that edge. You just include the edges in that order. So you take this edge and you include it, and then you take this edge and you include it, and then you take this edge, but then you realize that you don't want to include this edge because it would form a cycle. So you just use some like disjoint set union to check whether these 1 and 3 are already in the same component. So if they are, then you don't merge them, and then you take the one with edge 2, and there we go. So this would be, and the 6 again merges 2 already in the same component, so you don't use it. So this finds you one minimum spanning tree. So let's say we've got that now. We've got that minimum spanning tree. Got this one. This is, by the way, the third minimum spanning tree, other than these 2 for this case. So now we know that every edge on this minimum spanning tree is obviously on at least one minimum spanning tree. So for these edges, we know that they are on a minimum spanning tree. Now we need to find out for the other edges that aren't in this tree, are they in a different minimum spanning tree, right? So are they in a different one? And we can notice that we can answer that question like so. So let's say we take this edge. You can notice that if you consider the path in the tree between the nodes that this edge connects, the path in the current minimum spanning tree between them, if there is an edge on that path that has the same weight as this edge, then we can just swap them out. We can just swap that edge for this edge. So in this case, we can swap this edge out for this edge, or this edge out for this edge, and you'll still have a minimum spanning tree. So in that case, it's actually correct. So if we go back, if we draw something a bit more abstract, if we're considering one specific edge that isn't in the minimum spanning tree, if you consider the path on the minimum spanning tree between these guys, between the nodes that this edge connects, then all the edges on this path, so let's say this edge has weight like 7, all the edges on this path will have weight at most 7, because if there was an edge with larger weight, then if you took that edge out of the minimum spanning tree and put this edge in, this will obviously still be a spanning tree. It's quite easy to see. And this will be a smaller spanning tree. So we've got a contradiction. The original one wasn't minimal. So all the edges on this path will have edge weight at most 7. At most 7. So you'll have maybe 6, 2, 1, 7, 3, 2. Something like this. But so if there is an edge with exactly 7, then you could just add this edge to the spanning tree and take this edge out, and we'd have a new spanning tree, a new minimal spanning tree, because the total weight is the same, that now contains this edge. So in that case, if that's possible, then this edge is also, we can tell that this edge is also in a minimal spanning tree, in a minimum spanning tree. However, so we have a check now. We can check if that is true. If there is an edge on this path that has the same weight, then 7 is in a minimum spanning tree. But what if that's not the case? Does that mean this edge is not in one? Well, actually, it does. If all the edges on this path are lower weight, you can actually show that there is no possible way to give you to create an MST, short for minimal spanning tree, an MST that contains this edge. Because if you somehow found an MST that contains this edge, you can just show this somehow. So let's say we found an MST that contains the edge 7, right? We can show that we can do kind of the same thing to that tree as we did to this one, but the other way around. So we can remove this edge from it and add one of these, and it would just strictly improve that tree. Because all of these, like we assumed, all of these edges are lower than 7 in weight, and because this is a path, so these edges are all consecutive, if you took the minimal spanning tree, we assume there's a minimal spanning tree containing this edge. If you took the minimal spanning tree and deleted this edge from it, you'd be left with 2 components, and where this edge used to be between them, but we've deleted it. And now if we just walk along these edges, since they form a path between the endpoints of this edge, at least one of them will step across this void. And so whichever one that was, let's say it's this 6, we can just insert that into the minimal spanning tree, into the tree, and it'll become a new, even smaller spanning tree. So we've proved not only that. So what have we shown? If we've taken if we find a minimal spanning tree, if we find any MST, then obviously all the edges already in that MST are in at least one MST. And now, additionally, for any other edge not in the MST, if we just check whether the MST, the path in the MST between its endpoints, contains an edge with equal weight to this edge, then if it does, we've shown a way to construct an MST that contains this edge. And so, yeah, we have an MST with this edge. And if it doesn't contain such an edge, we've proved that there can't be an MST with this edge. So we've found an equivalence to this problem. So all we need to do now is construct the MST with, let's say, Kruskal's algorithm, which is what we just showed, and then answer this question for each edge that isn't in that spanning tree. So how do we answer this question? Is there an edge on the path that's equal, on the path between these two nodes in the tree that's equal to this value? So specifically, actually, we've already said that there isn't an edge greater than this value. So there can't be an edge greater than 7. So all we're checking is there an edge equal to 7, but there can't be one greater. So it's the same as checking, is there one greater than or equal to 7? And we can answer these queries like so. So if we have if this is the tree, so we've already constructed the tree, and there are edges between some of these nodes, and we have to answer queries based on those edges. So for each of them, we have to find something on the path between them. So let's forget those edges though. So we have the tree, and we have to answer queries of the form like take to these two nodes and give us the maximal edge on the path between them, right? Because that's all we care about. Like for this 7, we just care if there's another edge on the path that's at least 7. So we just want the maximal edge weight on the path. So here we have a tree and we have queries of the form, what's the maximal edge weight between these two nodes? And we can't just walk along the tree because that would be O(n) for each query, and the number of edges is too high here. So this would be O(n)m, where n is the number of nodes and m is the number of edges. And that in this problem is too high because the number of nodes is around 1,000, and the number of edges is around 1,000,000. So that's too high, or more than 1,000 and more than 1,000,000. But what you can do, instead of walking along these, well, actually, I say that's too high. With a good enough constant, you could actually pass some. It is possible to pass with this kind of solution, but it's very easy to just to sidestep this issue completely and just solve it in O(n)² by pre-computing this. So you just want to pre-compute for each node. You want to pre-compute the max distance to any other node, the max edge on the path to any other node, and that's just n². You can just pre-compute that on this tree in n². And as we said, because n is quite small in this problem, it's around 1,000. We can just pre-compute that by launching a DFS from every node. And yeah, that's basically it. So we pre-compute the max edge between every pair of nodes, and then we just query those between pairs of nodes. So that is the solution, or that is a solution. That is the intended solution. It is not actually the simplest solution. So it's still an interesting problem to discuss from this point onwards, but I mean, you can just stop watching at this point if you'd like to. But there is a cleaner solution than this. So this solution, like we said, is find some MST and then pre-compute these edge distances. But before I dive into that cleanest solution, I want to say that this also isn't the fastest solution possible, being at O(n) squared. There is actually a way of solving this problem if you're not allowed to use quadratic time on the number of nodes. So if the number of nodes is also, the constraint on the number of nodes is as high as the constraint on the number of edges. And the way you do that is just by answering these queries, instead of pre-computing the answers to the queries just for all pairs of nodes, you'd pre-compute them on smaller paths and combine them using binary lifting. So that's a cool technique. I won't go into that now, but it's basically a way of you're pre-computing answers to this, not for all possible paths, like from this node to every possible node, but you're pre-computing answers to all paths that are whose lengths are powers of 2, and also only vertical paths. So like not paths like this, but paths. So like from this node, you'd calculate for this one of length 1, then length 2, the length 4, and so on, just going up until you reach the root of the tree. So you'd root the tree as well arbitrarily. And then what this technique ends up doing is if you then want to query for 2 nodes, in this case, what we're doing is maximal edge, but you can use this technique for sums as well and whatever. If you want to query the maximal edge weight in between them, then you just use power of 2 jumps so you take the lowest common ancestor in the tree of these 2 nodes. So this would be the whole tree. The root would be up here somewhere, but for these, if we want to query for these nodes, their lowest common ancestor is here somewhere, and we can use powers of 2. So we can say we can divide this up into a jump of size 4, which is the largest power of 2 that fits into this whole thing, and then a jump of size 2, and then this is directly just a jump of size 4. And so we already have pre-computed answers to these three paths, and then we just take the max across the 3. But so basically that's another technique you can use to solve this more optimally. So instead of n squared, that would be like n log n plus e, something like that. Maybe e log e, actually, because you have to sort the edges for Kruskal and prim. So something like that would be n log n plus e log e would be the complexity for this graph. But what you end up with is what we said. So the pre-computed O(n) squared solution. Then we have the LCA solution, or the binary lifting solution, which is faster than that, although it does require some memory overhead, which the memory limit on this problem is actually very tight, so you have to be careful with this, but you can still get it to pass. But typically the memory limit on these kinds of problems isn't too tight, so binary lifting is often a nice way to do it. Again, not necessarily in this problem because this solution works. But so I mentioned there is a simpler solution, so let's go into that because that's really the interesting part here. The simplest solution is as follows. We've already got to the point where we realized that for any edge, all we care about is the path between the nodes in the tree. But we can generalize that. We can kind of ignore the tree altogether. So you can actually show that this idea works. If you have an edge that you care about, let's say I'm just drawing random stuff at this point. Let's say we have this edge, right? And again, its weight is 7 because that's just a nice number. So we have this edge. We now haven't even constructed a minimum spanning tree, but when will this edge be in at least one minimum spanning tree? And you can actually show that this, if you just consider all edges of weight less than 7, right? All edges of weight less than 7, and delete all all bigger edges from the graph and leave only the edges of weight less than 7 in the graph. So you'll have a bunch of nodes, and imagine these are all the edges of weight less than 7. So there's a 3, there's a 5, there's a 4, 6, etc. And we can just like keep going on this side as well. There's just a bunch of nodes. All these edges have weight less than 7. If there is a path between these two nodes with edges of weight less than 7, so this is no longer the minimum spanning tree that we constructed. We haven't constructed a minimum spanning tree. We're just considering all edges in the tree. But if there is if there is a path between these nodes using edges only of weight strictly less than this edge, then we can show that this edge will not be in any minimum spanning tree. With exactly the same argument that we already used earlier, by saying that if this edge was in a minimum spanning tree, we could knock it out and put one of these edges in, and strictly improve it. So we have a contradiction. And we can also show that if there is no such path, then this edge is in at least one minimum spanning tree. Because any minimum spanning tree, not including this edge, must include at least one edge on the path between, so the path between these two nodes in that minimum spanning tree must obviously include at least one edge with weight greater than or equal to 7. And so popping that one out and putting this one in wouldn't make the tree worse. So we've turned the argument we had earlier into an argument not about a specific spanning tree, but about the general graph. And so what we're saying now is basically, for each edge, all we care about is whether it's possible to connect its endpoints with edges of strictly lower weight. So we're talking about connected components here. And it's quite easy to simulate this, actually, if you're already building the minimum spanning tree with disjoint set union. With Kruskal's algorithm, this is quite similar to that. So all you want to do is set up a disjoint set union, a DSU, with data structure. So all the nodes initially are separate. And then you go through all the edge weights in increasing order. So you go through all the edges in increasing order. So let's say initially you take all the edges with weight 1. So this edge, let's say this edge has weight 1 and this edge has weight 1. So you add them both, and then so you just add the edges in this order, and you answer queries as you go, actually. So when we're adding this 7, if we have multiple edges of weight 7, basically, if we've already added all the other edges to the graph, kind of explained this badly, but let's say we've already added all the other edges to the graph with lower weights. We now have edges of weight 7 that we're adding next. And so there are probably multiple of these. So there's this one of weight 7. Let's say there's this one of weight 7, and there's this one of weight 7. There are 3 edges of weight 7 that we're about to add. What Kruskal's algorithm would do is it would just go through them in any order and start adding them. So it would arbitrarily assign priorities. But what we want here is, for all of them, we want to check, before we've added the other edges of weight 7, can we get through them, and are its endpoints in different components? So that's exactly what we're going to do. We're going to check, before we add any of these edges with weight 7, we just check. So these two nodes are in different components. That means this edge is in at least one MST. These two nodes are in different components, so this edge is also in at least one MST. These two nodes are in the same component, which means they can be connected with the edges of smaller weight. So this edge is not in at least one MST, in any MST. And then after we've done that, now we add all of these edges to the graph. I mean, this edge won't change anything because they're already connected. And then we repeat. So now we move on to edges of weight 8, and so on. So that is the idea. That's the final idea. That's actually the fastest solution. I mean, in terms of complexity and in terms of space, it's also the most compact. And this is just the nicest solution. So this is the solution to this problem, to problem pie in the sky. And this is just the cleaner solution than the other ones, but it's very slightly harder to spot, but it's just nicer. So yeah, there you go. I'll put the solution code as usual in the description. Yeah, that's it. See you guys in the next one. Hope you enjoyed it.